thank the organizers for the invitation to give this talk. And so the topic is galaxy-galaxy lensing. I like to call this actually, with a slightly more general name, halo shear. And the reason is that, well, what we're trying to do here is to look at a signal around objects, but these objects don't have to be galaxies. They could also be groups or clusters or actually anything else. All right, so the idea is that one is looking at the signal around specific objects, which we call lens. The overview is shown here. I'll talk about first theoretical developments, then I'll talk about the applications to the data, particularly Sloan data. I'll talk also about the cluster analysis, and then I'll talk some things about the future. If you want a bottom line, I would like to argue that halo shear or galaxy-galaxy lensing is a powerful alternative to shear, and in many ways perhaps even more promising, and so one should keep it in mind for the future. There's a long list of collaborators that I work with, that's shown here, and of course they've done a lot of this work. So what are we talking about here? So if we have distribution of mass in the universe, we'll have some sources, and these sources will generate shear on the background galaxies. And one can measure this by looking at the tangential distortions around these lenses. These lenses, as I said, could be galaxies, could be clusters, and so on and so forth. Now, this is particularly useful if you have the redshift of the lenses, because if, as you know, shear analysis is usually done in angular separation. Everything from the observer to the source adds to the signal. Whereas if you have a lens and you're looking at a shear pattern around the lens, then the contribution is only the contribution that is correlated with the lens, and as such one can have the lens redshift, and therefore one doesn't have to express the answer in terms of the angular separation, but one can actually express the answer in terms of transit separation from the lens, which of course is just the angular diameter times the angle. So that's one advantage. The second advantage is that the shear itself, one can express it in terms of the projected, so-called differential projected surface density, delta sigma over sigma crit. Delta sigma is the mean surface density within that radius, projected surface density within that radius, minus the surface density at that radius. Where, as I said, the surface density is just a projection of the density along the line of sight. And then the normalization factor is the sigma crit, which is just some combination of the distance factors, angular diameter distance factors. Here I expressed it actually in terms of moving distance, so that's why we have this 1 plus ZL squared. But basically, if you have the redshift of the lens and the redshift of the source, you can calculate this. Now typically we have the redshift of the lens if we do this on some spectroscopic objects. We have some redshift distribution for the source, and so this becomes a kind of average. The sigma crit is some kind of average over all possible redshift, over the redshift distribution of the source galaxies. All right, so one advantage therefore is that this is done in terms of actual projected density and in terms of actual projected distance and not angles. All right, so let me talk about theory first. When we look at the relation between galaxies and dark matter, we know that galaxies, trace dark matter on large scales, but even on large scales we do not know what their amplitude of the relation is, a so-called bias problem. So galaxies are a bias tracer of the dark matter, and we don't know what that bias is if we just look at the galaxy correlation function. This is shown here for various halos. This is a plot taken from some work we've done with Robert Smith, and this is these are just halos split by mass, and as you can see, the more massive halos are more strongly clustered. All right, so that's not the only problem, however. The problem is that this bias is not just a constant number. Well, it is maybe on large scales, but as soon as we go to intermediate scales, below tens of megaparsecs, it becomes scale dependent. So this is a problem of scale dependent bias. So from this one would conclude that, well, galaxy clustering has a very complicated relation to the dark matter clustering, and therefore that galaxy clustering in itself is not, does not provide useful information about the dark matter. And of course, that's the whole premise behind weak lensing. That's why, you know, we're all here, I guess, because weak lensing traces dark matter directly. However, let's look at the same thing in terms of the cross correlation between galaxies and dark matter. And we see a very similar pattern here, that again, the more massive halos are more strongly biased. All right? And again, on large scales, this bias is relatively scale independent, and on small scales, this becomes scale dependent relation. This is now cross correlation between galaxies and dark matter. Same comment applies. You know, from this you would not be able to learn much because there's this complicated scale dependence and so on and so forth. Now, the interesting thing is, however, that if you look at the cross correlation coefficient between the galaxies and dark matter, and that's shown here, you find that this cross correlation coefficient appears to be universal. That appears basically to be independent of the halo mass. This is shown here again from the same simulations, and you see cross correlation coefficient is very close to unity on large scales. On small scales, it deviates from unity, but not by that much. You know, even at 10 megaparsec, it's still only a few % away from unity. And then it deviates, but you can see basically it's the same for all the halos, at least within, at least outside the virial radius. Then inside the virial radius, you have the exclusion, and you no longer can apply this. Exclusion just means basically that two halos cannot be closer to each other than twice the virial radius. So, you know, below twice the virial radius, you should have no correlation. If you talk about halos, if you have galaxies, of course, then it's more complicated because you have satellites inside the galaxy, inside the halos, and so on and so forth. Whereas in small scales, in the cross correlation between halos and dark matter, what one is seeing is the dark matter profile. I'll talk about that later. All right, so this coefficient appears to be universal. Moreover, we have a good theory about this cross correlation coefficient, perturbation theory. I'm not going to go through these equations, but let me just summarize. It's just a simple first-order perturbation theory. You know, basically there's a derivation here, but the bottom line is the prediction for this cross correlation coefficient is extremely simple. There's a coefficient, and there's it just says it's 1 minus you know, coefficient times the correlation function itself. And that's a very simple prediction that actually, I'll show later, agrees very well with this simulations. All right, so there's a problem, however, when we talk about lensing, indirectly, why this cannot be directly applied to the lensing. It has, the problem is the one that I already mentioned before. The shear is measuring delta sigma. This is average projected density minus the projected density. This average goes from 0 to r. As I have said here, shown here, the cross correlation coefficient is actually very different from 1 on small scales. And this differential surface density then takes the small scale information and, you know, maps it to any scale, because this mean surface density you know, takes information from 0, from small scales to a given scale. So instead of that, we introduce a new statistic which cancels the small scale information, which is where this is the most problematic. We call it epsilon, and basically, you know, it's just some combination of this delta sigma minus delta sigma at a given radius times this. And you can show that basically this only then has information from some r0 to r, no longer from 0, but r0. So if you choose r0 to be larger than twice the virial radius, then one eliminates this problematic information on small scales. So we tried it on simulations, and this is the example for the cross correlation coefficient. If you don't do this, if your r0 is 0, you can see it's very different from 1, cross correlation coefficient. On the other hand, if we do this from r0 equal to 3 megaparsecs, in other words, we eliminate information below 3 megaparsecs, then we get, in simulation, we get this red line. This is the cross correlation coefficient in simulations, and the solid line is the theory that I've shown you before. They have a perfect agreement. First of all, what is important is that cross correlation coefficient is, you know, 2% different, only 2% different from 1, even at 4 megaparsecs. You know, 10 megaparsecs, it's within 1% of 1. It's extremely close to 1. And second, we have a theory for it. Perturbation theory works very well. So, if you have, therefore, if you know what the cross correlation coefficient is, then you can invert this relation. What is cross correlation coefficient? It's the, you know, a cross correlation divided by the square root of the other correlation products. So if you measure this and you measure this, you can invert this, and you know this, you can invert this relation, and you can measure, therefore, the dark matter clustering by doing this combination. So we tried this on the simulations, and the dashed is the simulation result, And blue is the nonlinear prediction, and as you can see, the simulations and nonlinear predictions agree very well from the power spectrum. And you can see also that linear power spectrum is not in a good agreement. In other words, we have nonlinear effects here that we have to include using MOD simulations. But the bottom line is this reproduces the dark matter clustering power spectrum. So we tried this on several different simulations that Robert has run, and it always works. And so, for example, when you do this on these various simulations, we can, in each case, we reproduce the dark matter power spectrum, and you can see basically there are large differences between these simulation predictions, and in each case we reproduce the predictions. If you want to know in terms of the power spectrum kernels, K kernels, basically if you talk about a 5 megaparsec scale, the kernel peaks at K of 0.5. So in other words, we're really picking high K modes, which are nonlinear. At 20 megaparsecs, we're picking something around between K of 0.1 to 0.2, and so it's much closer to the linear scales.